have a familiar face, Kenda Knowles, coming to talk to us, who I guess many of you will recognize. And she's going to tell us today about the MeerKAT Galaxy Cluster Legacy Survey. So over to you, Kenda.
Cool, thanks, Tony. And thanks very much for inviting me to give the seminar. I think particularly there were a lot of conferences in March, so many people may have seen a much shorter version of this. We'll see how it goes. So I can't see the full list of names who are attending, so I'm not sure if there's any non-cluster people here, but for those who are, I'll just give a brief introduction to clusters, why we should care about them, what you can do with them in the radio, and then give a hopefully unneeded intro to MeerKAT, and then I'll go into the core content of the survey. So galaxy clusters are the largest gravitationally bound structures that we know of in the universe. They're typically found at they are found at the nodes of the cosmic web. So this background image here is from the Millennium simulation, showing the growth of dark matter in the universe, and clusters are found at the intersection of a bunch of filaments. And the masses cover quite a range, anything from 10 to 13 to 15 solar masses, and they are obviously made up of constituent galaxies. So the galaxies are not the only thing that's in there. There's several different components that make up the mass budget. So this is a beautiful color composite of the bullet cluster, courtesy of NASA, showing the different parts of the mass contributions. So in blue, we've got dark matter. So that is the majority of the clusters. It takes about 80% of the mass. You can study dark matter in clusters through things like gravitational lensing and use it to probe things like cosmological models and maybe even the precise properties of the dark matter particles themselves. Then you've got the color in this image, the RGB, which is the galaxies and the stars. And you can study, one of the popular things to study with clusters is the effect of environment on the actual galaxies. So you'll have many, many galaxies within the actual cluster, but then you do also have field galaxies or galaxies infalling along filaments. And how does the dense environment of the cluster actually affect any of the evolutionary properties? And then one of the last things is you have the intracluster medium, which is a hot gaseous plasma and takes up about 15 to 17% of the mass budget. And this is, pervading the entire region. And it holds a lot of information about the merger history of the cluster. So for example, the bullet is quite a well-known merging system. And that's, you can see a lot of that in the distribution of the various components, but within the actual gas itself, you can see things like shock fronts and the fact that it's bimodal. And by studying this intercluster medium, you can study things like turbulence, shock physics, and to actually figure out, for example, during a merger, which is one of the most energetic processes since the Big Bang, where does that merger energy go? How is it distributed throughout the cluster into the various components? So now if we're just looking at the radio, so obviously that image that I showed here of the bullet, you've got optical images of the galaxy, you've got gravitational lensing analyses, which can tell you where the dark matter is, and the gas you can see in the X-ray. You can see it via the Sunyaev-Zeldovich effect through the inverse Compton scattering. And in some cases, you can also see it in the radio. And obviously, some of the galaxies themselves shine in the radio as well. So in the radio regime, I'm going to just go quickly through a few of the research topics that people are studying. It's by no means an exhaustive list. But it is some of the things that you can do, particularly using the MeerKAT data that I'll discuss later. So the first one that I'd like to talk about is the AGN feedback. So this is, in many clusters, you have the brightest cluster galaxy, or any radio loud galaxy within the cluster may have an AGN. So that's the active galactic nuclei with the nuclear physics in the black hole, and you get radio jets emanating from the galaxy. So in this figure here, the blue is X-ray and the red is the radio. And I can't remember when this paper was from, but some cases have been found where you have cavities within the X-ray, which weren't really well understood until someone decided to look at a composite with the radio, and these jets emanating from the AGN in the center, they are often quite well aligned with these cavities. And through systems like this, you can study the process of AGN feedback on the cluster and on the galaxy itself, where you have a cyclical process of the environment being heated up by the AGN jets and stopping it from cooling and condensing, as you would expect when there is no AGN activity. Then you can also use radio galaxies to study what we call the ICM weather. So this is, you can use things called bent-tailed sources. So here we've got a narrow angle tail, a wide angle tail, and a head-tail, just basic head-tail radio galaxy. And so these are the typical FR1 or FR2 source, where you have an AGN and the jets, but there is some dynamical process. This galaxy is moving through the medium, through the intercluster medium, and there's, for example, ram pressure stripping, which is allowing the jets to be bent backwards and sort of stream behind. And then the jet emission is actually, in some cases, interacting with the medium in other complex ways. So, for example, this head tail, there's some interesting complex morphology looking at these jets. And so studying these types of sources and often coupling them with simulations, you can identify the dynamics of, for example, the cluster merger, what components there are, and basically just the details of the dynamics. Then in terms of population studies, I mentioned this before, using a cluster environment to study the effect of environment on galaxy evolution. So one of the things, obvious things to study there is the star formation rate. There's also the far infrared and radio correlation, and the idea, standard idea before has been to study field galaxies and then study similar galaxies but within the cluster environment, measure intrinsic properties, and for example, star formation rate. You can see here, so here the blue is the field galaxies outside of the cluster environment, and the black diamonds are the ones in the cluster, and you have a lower average star formation rate, particularly for the lower redshift clusters, than you do within the field. So what is happening to quench a star formation rate within a cluster? And then one thing I forgot to mention in terms of what's in a cluster, so I mentioned the dark matter, the gas, the galaxies. Pervading all of that, you also have magnetic fields, which are obviously very difficult to observe directly. But if you have polarization sensitive radio data and you're observing synchrotron emission, so synchrotron emission is where you have highly energetic electrons spiraling through a magnetic field and giving off photons. So the synchrotron emission, it requires magnetic fields to exist. So by studying it, you can infer properties about the magnetic field that is causing it, essentially. So one of the ways that you can use the emission and radio galaxies actually to study the magnetic fields within a cluster themselves is something through Faraday rotation. So this is where, so here we are in the observer, you have some background galaxy, and along the line of sight between the two, you have a cluster of galaxies. And the emission from this background radio galaxy, and the polarization is going to get perturbed by interacting with the cluster. And if you have enough background galaxies, you can actually use this to probe the magnetic field structure within the cluster itself. This is generally quite difficult to do because the polarization of radio source is generally a lot fainter than its intensity. So finding bright polarized sources has been quite rare, and to then find enough of them in a particular patch of sky has been challenging with previous radio telescopes. But with the next generation, things like MeerKAT, etc., the sensitivity has improved, and we can, this is becoming a more viable study area. And then that was a bit too trigger happy. The last one that I wanted to mention is the diffuse cluster radio emission. This is where most of my expertise lie. And what this is the synchrotron emission from the intracluster medium itself, rather than individual radio galaxies. They're typically large scale. So in all of these, what you see here, the color is the X-ray emission, and the contours are the radio emission. And you can see you have a variety of different morphologies. And depending on the morphology, the position with respect to the cluster center, and also the polarization properties, you have different classifications of diffuse cluster radio emission. The larger structures, so these are halos, and the relics are linked to major mergers, and typically massive ones, although there's a really nice paper that came out, I think this week or last week, on a very low mass detection. So with our sensitive instruments, if we go looking, we can find them. But then you also have radio mini halos, which tend to be smaller and are linked to the BCG of a cool core cluster, so in a more dynamically relaxed system. But studying these types of structures, you can study the physics of the merger and try and understand the physics of particle acceleration, because one of the common aspects of these types of emission is that the decay lifetime for a synchrotron photon is shorter than it would, it can't travel the volumes that we see this emission cover before it's lost energy. So there has to be some mechanism in place to be pumping energy into the system or to the electrons to keep them at the relativistic speeds needed to produce synchrotron emission on these volumes. So that's quite a wide range of topics, and there's various requirements that you need from your radio data to study all of them, but just keep these in mind for the next part of the talk. So hopefully I don't have to go into details about MeerKAT. Hopefully now everyone is quite familiar with what it is and how wonderful it is. But in case there's anyone on this call who isn't familiar with it, so MeerKAT is an interferometer with 64 dishes that's in our South African Karoo, which is probably one of the most radio quiet places in South Africa. And it is the most sensitive radio instrument at its frequency in the Southern Hemisphere, particularly at L-band. And it's very, very powerful in a number of ways, mainly because it has extremely good surface brightness sensitivity. And the reason for this is the actual design of the array. So if you're ever reading papers and they're talking about the core of an interferometer, so MeerKAT has its 64 dishes are spread out in a somewhat pseudo-random pattern. And the inner core, which is 1 kilometer diameter, is where about half, over, was it 2/3? I can't remember now, but where most of the antennas lie. So this means you have a lot of short baselines. So that a baseline is the separation between two antennas. And in terms of interferometry, you have a reverse relationship between distance between antennas and the scale on the sky to which you are sensitive to. So these small spacings give you very, very good sensitivity because you have so many of them, they give you good sensitivity to large scale structures on the sky. With MeerKAT, that's up to about 10 arc minutes, after which you start resolving out emission. But at the same time, what's important for a lot of the galaxy studies is that you need to be able to see some fine scale structure. So we have radio all sky surveys, well, not all sky, but we have a radio sky survey, for example, the SUMS survey at 843 megahertz in the Southern Hemisphere. but their telescope resolution is 45 arc seconds. And you can't really, it becomes very difficult to see any fine structure for anything that's not very nearby. So with MeerKAT, it has its longest separation of 8 kilometers, and we have this ring of outer ring antennas, which is giving you 6 to 8 kilometer baselines, which help balance the small baselines and give you this simultaneous sensitivity to emission, but also sufficient resolution to do galaxy studies. So this is where I get to the Cluster Legacy Survey. So this is a program of observations on galaxy clusters that the SARAO Observatory started in 2018. So they observed about 115 targets between 2018 and 2019, from June to June. Everything is in the MeerKAT L band. So I've given the frequency range there. It's the reference frequency is at about 1.2 gigahertz. So these are also long track observations. So they're good and sensitive, with most clusters having anything between 6 to 10 hours on source per cluster. And everything has been observed in full polarization. Then of the 115, they were observed in essentially 2 subsamples. One was radio selected. So this was where they targeted clusters that had been observed before in terms of diffuse cluster emission. And so that makes up about 1/3 of the observations were radio selected targets. And then in order to have a subsample, or at least some clusters that weren't necessarily biased towards diffuse emission detections, they also selected clusters from the MCXC catalog below a declination of -40. So although it's a very, very powerful sample, and 115 targets is nothing to scoff at, and they're good and sensitive, it is not I do have to make the disclaimer that it's not a homogeneously selected cluster sample. There are subsamples that you can create that have, that are homogeneous, but the full sample of 115, if anyone wanted to do statistical studies on that, it should be carried out with caution. I will also say that there are a handful of higher redshift systems, but these targets are dominated by lower redshift systems, and that's an effect of where the clusters were taken from. Being from typically diffuse cluster emission has been studied in high mass nearby systems, and X-ray selected. There was a luminosity restriction as well, so you're generally picking up the brighter stuff nearby. And so I say the full polarization, not everything at the moment has been calibrated for polarization, but I mention it here. So the main point of this cluster legacy survey is that it will be a legacy survey. And by that, I mean that it will be made public to the astronomical community, or I suppose to anyone if there was, it's completely public access. But the observatory really would like the community to be using these products for their own science. And the goal is to make MeerKAT data accessible to as many people as possible. So there has been a survey overview paper that has been prepared. And when that is published, all of the legacy data products will become public with that paper. So what these products are is the raw visibilities for anyone who wants to start from scratch and maybe do their own imaging, or they have their own resolution requirements, etc. But then we also have a set of image products that will be made public to the community. So the first set of are basic images, and these everything was done using the OBIT pipeline from Bill Cotton at the NRAO. So the basic image product is a 16-plane cube, and it includes total intensity and spectral index, which are fitted together. And then the other planes are individual frequency planes. two of which are blank. And these are full, the basic products are full sky. So they're about anything between 1.5 to 2 degrees across of the sky on, centered on the cluster pointing. And so these basic products are really good for source finding because the noise is more uniform, and they're really good for searching for targets of interest for individual study. Then we are also providing a set of enhanced products. So these are at both the full resolution, which is about anything between 7 and 8 arc seconds, and also convolved 15 arc second resolution for people who are interested in improving surface brightness. And the key difference between the enhanced and basic products is that the enhanced are primary beam corrected. So this means that for example, things like flux densities can be trusted within these images, but it does show a smaller patch of the sky. These are 1.2 by 1.2 degrees square. And they're separated now into two different types. You have 5 plane cubes, which have total intensity and spectral index, plus their uncertainties, and then a chi-squared of the combined fitting. And then you also have frequency cubes, which are the 12 non-blanked frequency cubes from the basic product. So as I said, the data is quite sensitive. It's there's a range of sensitivities, but in general, most of the cluster images have a RMS noise of between 4 and 7 microjanskis per beam, which is really good. You're getting very high source counts and source densities. But the one caveat I need to mention is that none of these images have had any direction-dependent calibration applied. So there are still bright source artifacts in some of the images. So that's the image products. And then the last legacy product is various source catalogues, which I'll go into a bit more detail. So I just want to pause on this background image for a while. This is this is a patch of one of the cluster fields. And you can I've edited the scaling here. So basically every single red point that you see is a galaxy. And you can see that in particular, is a really nice and sensitive image. And you can see that you're picking up fine scale structure in these sort of strings and filaments, but you're also picking up the more diffuse. So for example, these are lobes of a dying radio galaxy. And you're picking up regions of diffuse emission, but you're also picking up some weird and wonderfuls. There's radio galaxies in here with a bunch of different morphologies, ring sources. But here's an example. This is a bright, couple of tens of millijansky source within the field, and around that source you have these radiating artifacts because of the ionosphere and effects of the primary beam that haven't been calibrated for. So these are the direction-dependent calibration areas that you will see in some of the images. So now just go on to some of the more details, some of the capabilities of these data, since we do want the community to use them. So I've mentioned this a few times in terms of MeerKAT surface brightness sensitivity. And here's this top panel is just showing you an example of what can be done with these data. So in the middle panel here, you see a full resolution image. It's a cutout from one of the cluster fields focused on the cluster themselves. And you can see it's dominated by compact sources. If you know what you're looking for, there do seem to be some regions of fainter, more extended emission, but you can't really disentangle them at this stage from the point sources. So typically, if you are interested in faint emission, your standard go-to procedure to improve your sensitivity is to convolve to a larger beam. So what you see here on the left is this patch of sky convolved to 20 arc seconds. Sorry, 25 arc seconds. And here you can see this region where the faint emission was is now a lot brighter, But because of MeerKAT's high source density, you now run into the problem where you have a blending of the individual compact sources when you've convolved to larger beams. So now you hit confusion because of the blending of the compact sources. One way that you can get around this, particularly if you only have images to work with and not the actual visibility data, is you can apply a filtering technique where this original image is separated into fine scale and large scale structure, and that the boundary between what we define as fine and large is up to the user, but typically you get the most reliable results when you use around three times the actual size of the beam. And when you do this and then you smooth it slightly just to clear up the rough edges, you can get an image like this, which is the large scale image, where essentially all the fine scale structure has been filtered out. And now you can quite readily pick up the regions of that extended emission and even to some extent the morphology. So this is something we've implemented with the data in many cases, but these filtered images are not being made public at this stage. It's a very, I'm happy to discuss it with people who are interested, but it's a very quick Python procedure to get this type of image. So that's surface brightness sensitivity, and sensitivity on many scales, both fine scale and large scale. The next thing is that for the brighter sources, because of MeerKAT's wide bandwidth, you can calculate in-band spectral indices and actually create a spectral index map without having to go and get new radio data at a different frequency, which is typically what has been needed. So I mentioned a few times that the intensity and the spectral index, when the maps were being made, these were fitted jointly. And so in both the basic and the enhanced images, you have a spectral index plane that you can look at. And for, as I said, for the brighter sources, so this tends to be of signal to noise of 10 or higher. And that's where you can get a reliable spectral index. This is an example of a wide angle tail in one of the cluster fields. And you can see the core has a somewhat flat spectrum, a little bit flatter than what we'd expect for AGN. But you can actually see through the diffuse, the much fainter and diffuse emission of the lobes, you can still get reliable spectral indices and start seeing where there are different populations of electrons, and that will help you disentangle the physics of what's happening in this particular structure. And then I mentioned polarization. About 40% of the fields have been calibrated for polarization and will have polarization products. So that's QU cubes along with the Stokes I cubes being made public. Excuse me. So this is a rotation measure map for one of the very large scale diffuse sources in the survey. And there's some guidance within the paper of any sort of caveats you need to know about for polarization. Essentially, so rotation measures, you can calculate rotation measures, you can look at the polarization vectors, but polarization intensity should be used with caution in particular cases. But for those who are interested in polarization, there are 40% of the fields that have that available. And then lastly, quite an interesting use case was this is obviously a continuum project initially, but a small group of people within the collaboration have gone back to the visibilities and have shown that you can actually do some interesting H1 science with these data as well. So that should be kept in mind if you're an H1 person, that these data sets, the visibilities can be mined for H1 science as well. So going into a bit more details of what the collaboration has been doing. So as I said, this is a legacy survey that the key goal is to get the MeerKAT products out to the community so that the community can use them for their own science. But while we've been preparing the overview paper, the internal collaboration has also been starting to do some science exploitation. And so these are the things that I'll go through now. So the first one is some source catalogues, and this is creation of catalogues that will become public to the community as well. So we've created a compact source catalogue from all the cluster fields, and this is focusing on the PyBD. We use the PyBDSF source finder, and the compact source catalogue contains only those sources that had a single Gaussian source fit. So they're not necessarily point sources, but they are compact. And so this is quite a large catalog. We have 626 plus thousand sources within the catalog. You have a median of about 6,000 per field. Within the maximum one that I found was about 8,600. So that's a lot of galaxies, all with primary beam corrected flux densities, surface brightnesses, and source sizes. So to get this catalog, as I mentioned, you have some of these direction-dependent artifacts in the images, and in some cases, these artifacts confuse the source finder. And so around bright sources, you could get a high fraction of spurious source detections. So as a first release catalog, the catalog that we're releasing has undergone some automated artifact excision, where regions around the bright sources have been, all sources within a particular region around the bright source have been removed. And this takes care of most of the artifacts, but it does remove a small amount of the real sources. And in our checks, this looks like to be about 2% loss of real sources in the whole catalog, which is something we can live with at this stage. We have also compared our flux densities with other surveys. As a sanity check, we compared them against NVSS and SUMS, and both of them are in fairly good agreement with the MeerKAT flux densities after scaling them to 1.28 gigahertz. We have found that the MeerKAT flux densities are about 6% lower than in the other catalogs, but they are within the uncertainties of the flux densities. And then the other catalog that we have that's going to be public is an optical crossmatch catalog for both Able 209 and Able S295. So these two clusters were chosen as test cases because they have decals coverage. And so we have an optical crossmatch catalog for both of those clusters and an extended source catalog for these two. So in this case, what I mean by extended are these multi-component type sources, which generally have to be visually identified, and all the components visually identified, along with a likely optical host. So it is quite a time-consuming process, which is why we've only done it for 2 clusters so far. But here's an example of one of the extended sources in the Able, I think it's the Able 209 cluster. And this is showing a case of, multiple components, where in this case, it may actually be a conjunction of 2 different sources, where you have a FR1 galaxy with its core over here and the lobe there and the lobe ending here. And then this structure here is actually likely to be a wide-angle tail galaxy with its core and bright lobes. And these magenta circles just show regions where there's other radio sources with optical counterparts, showing how difficult it can sometimes be to figure out which galaxy belongs to which radio emission. Right, then on to diffuse cluster emission. I'll go through this quite quickly. This is just an example to show you what we've got. Of the 115 clusters, 62 of them have some diffuse emission detection, and it's 99 detections in total, and 56 of those are new. So it's a really good return in terms of diffuse emission cluster studies. Here's an example of one of the ones that we found, which is a new double relic and halo system. or it's actually multirelic. So you have a lovely strong relic to the southeast here with a lot of filamentary structure, and the brighter regions we've been able to get reliable spectral index information, which can help study obviously the physics of this. There's this complex northern relic, which is not clear whether that's got any relationship to individual galaxies, but what was really interesting was picking up this very faint radio halo. So the blue here is using that filtering technique that I mentioned earlier. And we pick up a lovely large giant radio halo, but on the edge of it, we see this sort of curved relic structure, which is, in terms of directional morphology, a mirror of the southeast one, which may reveal a faint position of a very faint shock, which is not seen in the X-ray. And so maybe deeper X-ray is needed or something like that. Then we also picked up some clusters which just have very strange morphologies, and we don't actually know how to classify the diffuse emission. So again, here the blue is from the filtering. This is a cluster, so this is MAX J0520. It was studied before in 2014, and it actually found that there was a companion X-ray cluster to the southeast of the main one, and in NVSS reprocessing of NVSS data, there was some sort of patchy emission found in these green regions. And when we look at this cluster with MeerKAT, and we do some of the filtering, we pick up a lot more extended emission, and all the extended emission seems to be linked rather than being completely disparate. So for example, here in this region, here it seems to be a filled bubble of radio emission that for diffuse emission, we're typically expecting to see things like relics or halos, where halos are nice and centered on X-ray and relics are on the peripheries with sort of narrow structures. And so these structures here don't really conform to anything that we know of so far. So this will be a really interesting system for follow-up study. And then in terms of radio galaxies, there's a lot of radio AGN with a wide variety of morphologies. I'll just show two examples. So this is one that I really like. It's within, quite close to the center of a cluster. And the question that we ask here is, well, okay, is this one radio source, or is this a conjunction of two radio sources, maybe just in projection, that they might have nothing to do with each other? And if they are two sources, where does one end and the other one start? So on further investigation, the source, so there is actually a radio core here that isn't visible in this image. But this galaxy here and this galaxy here, A, both, these are both radio galaxies, or rather have radio emission, but they're also individual WISE galaxies, which is what led us to think, well, maybe there's more than one source here. But even within the source itself, there's a lot of very interesting morphologies of, it looks like a tailed galaxy, but the tail itself seems to have periodic ribs. There's also tethers between two bright regions. And so here we looked at the spectral index map of the region. Luckily, it's bright enough that we can do this to try help us identify whether these are one source or two. The fact that where galaxy A is over here does have a different spectral index, a little bit flatter than the stuff on either side of it, does indicate that there is a radio core there. But unfortunately, it's still not clear from this gradation from, as you go from right to left, you have a steepening of the synchrotron spectrum, and all of this is very similar. And so it's still currently kind of difficult to figure out if these are two sources or not. So again, further investigation. And then I just wanted to mention, in terms of the surface brightness sensitivity, we've used it a lot for diffuse emission in galaxy clusters, but it's also really powerful for picking up dying radio galaxies. So these are galaxies where you had AGN activity, but this activity is now stopped for some reason. Nuclear activity in the black hole is switched off. And so the radio emission that was being produced and streamed out in the jets, there's nothing to keep powering it. So these lobes eventually die off and they become fainter and fainter. And we think we've found at least 2 within the survey. Excuse me. So in terms of, so those are individual galaxies and AGNs rather, you can also do star formation studies. And a big chunk of this has been led by Matt and Cabello at UKZN on the star formation rates. But we've also had people looking at the radio far IR correlation within Able 209. And Matt and Cabello so far have looked at Able 209 and will be extending the study to other clusters in the survey. So those are really nice population studies that you can do with the data. And we also have, in terms of individual star-forming galaxies, we have some really nice examples of nearby spirals that are being picked up where, as expected by now, you can see for example, the disk is much larger in the radio than what you pick up in the X-ray. I mean, sorry, not the X-ray, the optical. And then finally, as I said, there's a group that's been doing some H1 science with the data, and we've had some nice results now. They've looked at some H1 mass distributions of different clusters. They've been doing source finding within galaxy environments. So, for example, here you can see you've got some gas stripping happening. The H1 gas is being stripped off of that galaxy within the cluster region. I think this is Abel 194. We've since realized that we got really excited about this blob because it matched up really well with the lobe of some bright AGN in the region. But on further investigation, it's been identified that this is an artifact. So again, a really good reason to always self-check your results. But one of the really nice results that I think has come out of this is that they've found a new H1 group that was not previously known within one of the cluster fields. That they only looked at 4. So they obviously chose them really well that they picked up something. So this is a galaxy group that has about 26 individual H1 components. So yeah, I mean, H1 science does take a lot more work because you have to be working from visibilities themselves. But these are really nice demonstration examples of the types of H1 science you can do with the data. So then just to summarize or finish up, I hope I have convinced you that this legacy survey has a very broad range of science applications. It has a wide range of capabilities which allow for the different types of science. Key ones being sensitivity on wide range of scales and spectral index measurements for the brighter stuff. So the collaboration has already started on some science exploitation, but the goal here is definitely not to have the collaboration dominate everything. We really do want the community to get use of these. And there's lots of scope for community use over the 115 different clusters. So I'm happy now to say that the overview paper, which has been quite a labor, it's been about 1.5 years since we first got together to talk about what are we going to do with this data. And this overview paper has now been submitted. And so we're waiting for the review process. And just a reminder that, again, on publication, all the legacy products will become public. And if you have any other questions, there's either of my email addresses to contact me on. So yeah, thanks very much for your attention. And hopefully I've inspired you to use MeerKAT data in your future.
Great, thanks, Kenda. That was very interesting. Certainly quite an exciting product you guys are unleashing onto the community here.
Well, thanks, Kenda, for the nice talk. Just a curiosity about the study of the diffuse emission, when you talk about the diffuse emission in radio. So is it always synchrotron emission that people study, or has there been any attempt to focus also on the thermal radiation from clusters? So like from the thermal Bremsstrahlung, or maybe is it too faint at those frequencies compared to the synchrotron?
I think at one point, well, I guess it's not 1.4, but 1 point above 1 gigahertz, I think you would expect it to be a lot fainter than the synchrotron.
Okay.
And I mean, I don't want to tell a lie here, but at least from my knowledge, it's synchrotron emission that people have studied so far. I guess that doesn't necessarily mean that there isn't thermal emission there to study, but I think at the frequencies we've been working at, the synchrotron is dominating.
Okay, so does it also have to do with the fact that electrons there tend to be relativistic? So most of the emission could be indeed synchrotron. So the high energy, the very high energy of these ICM electrons.
Yes, so I mean, that's what we've found with the diffuse cluster emission, is that it's coming from these relativistic particles. And that's also what's generated the theory, the formation theory models, is that you need to be keeping the particles at relativistic speeds in order to see the volumes. And when you don't, it dies off. So.
Okay, thanks.
Perhaps I can ask a kind of naive one. In the beginning, you showed a picture with some sort of X-ray emission, and you spoke of the radio jets punching holes in this X-ray emission. Yeah. So the X-ray emission is thermal, is that right? And,
yes.
And then, is it known what the jets are doing to the thermal gas that's making it not emit in the X-rays anymore when they're interacting? Or?
So, okay, so a disclaimer, that's not my field of expertise, but from my understanding is that, so obviously the non-thermal emission from that you end up seeing in the radio is being shot out at speed from the galactic nucleus. And it's actually, that is what creates the cavity in the X-ray. So I think it's a case of it's moving the thermal out the way. Yeah. So it's creating these bubbles. You have the radio bubble filling the cavity in the X-ray.
Okay, good. I see. Thanks. And one other one, maybe while we wait for someone to ask a question, you spoke about extracting the diffuse emission from some of these images via some process. Is it like a Fourier transform process where you just...
No, so this filtering, so the standard way that you would do it if you had the visibility data is often to only image the small scale structures, so the point sources, and then remove that in the Fourier plane, and then re-image so that you're only left with the short baseline information.
Right, so you remove it in the frequency domain. Is that right? When you say remove it in the Fourier plane, do you mean in the...
So in the actual visibility space. So your image is in the image space and your actual radio data is in the visibility space. So that's your UV coordinates. And it's in the UV data space really, because what you're doing is the layout of your array will tell you what your UV coverage, so what range of scales in the UV in the Fourier plane you actually cover. And that's the short spacings relate to the large scales in the image because it's that Fourier relationship. So you would typically image only the long spacings, so that, and you create a model essentially for point sources and you remove the model in the visibility plane. But you can't do that if you don't have the visibilities. So for example, a lot of people who just want to download the images for this, there's been a filtering technique, which is, so it's really quite simple in terms of the actual applications. It's just doing box filtering on your image. Okay. And you tell it basically that delineation of scale. It does mean that anything that's close to that scale, some will be left in the small scale image and some will be left in the low. But yeah, we found it to be really useful to be able to, even just in terms of source discovery, to just run it on the images, and you get out this, you'll basically get a point source image out and a large scale image.
Okay, cool. Thanks. That makes sense. Yeah. I see Tanisha Pillay has asked a question here. She says, not sure if I missed it, but will you be working on next? What will you be working on next with the GCLS data?
So there are several other follow-up projects. So I'm involved in the diffuse emission. There's a diffuse emission paper that we want to put together, which goes into things but more detail than the survey overview. And I'm also working with a student at Rhodes looking at high redshift, looking for high redshift galaxy candidates, which is then on the source, the galaxy source side of things rather than diffuse emission.
And I see Kavi has a question. He's got his hand up. Kavi, do you want to go ahead?
Yeah, thanks, Kenda. That was great. Wouldn't I guess if there's interesting science that is identified or interesting objects, targets identified in the sample, is there an opportunity? I mean, I guess within the team that's kind of coordinating the project, would there be opportunities to apply for follow-up, you know, to extend that through? I mean, open time, I guess, is quite competitive, but
Oh, I see.
Yeah.
Nothing. You could definitely apply.
Yeah.
It wouldn't be, the date would, the time wouldn't be guaranteed. But for people within the collaboration, if there was follow-up data, then I think now that the survey paper has been submitted. So initially this was a part of the discussion back when the open time call was out, so September last year.
Yeah.
And the decision was made that you couldn't, particularly when you were part of a collaboration with people outside of the MGCLS collaboration, is that you couldn't use any proprietary information to support a new proposal.
Right.
So I think now we should actually have another discussion with the managing committee and see, now that the actual survey paper has been submitted, even though it might take a good, a few months to get it published, whether that will be allowed for the next round of calls. I think, again, it'll obviously, I think the concern there is that you don't want to bias a proposal compared to the general public, because the general public doesn't have access to it. I'm not sure. I personally don't see a problem with it, but I don't have the final say. Yeah. So, but it's something I can bring up with the management committee.
Yeah, I guess the question asked another way is, would the management committee be looking to team members to coordinate and say there was a interesting target to follow up further and put those in through the auspices of the MGCLS, or will the MGCLS basically kind of come apart now?
I think so. The MGCLS is still going to be, the collaboration is still going to exist at the very least until a few months after publication, because of all the follow-up projects that are already ongoing.
But after that, there's no desire to keep it together. Okay.
No, I don't think so, because everything's going to be public. So then it's everyone, they can do whatever they want with the data rather than having to be overseen by.
Okay.
I think it's as long as, that's actually a very good question. I will bring it up with the management committee, because in terms of the timelines of when does proprietary access end, I mean, it's not going to end a week after publication, because new people would only have had a week to look at the data. But maybe after 6 months or something after publication, or 3 months.
Okay, cool. Well, thanks.
Okay, I think, well, since we're 3 minutes over time, we should probably call it. Thanks again, Kenda, for
cool. Thank you.
Talk and pushing through with what sounded like quite a sore throat.
That's just an annoying cough.
Yeah, cool. Great. Well, thanks everyone.
Yep. Keep well in Durban.
Yeah. Enjoy your time. See you.
Bye.
Bye.